Hello my friends, welcome again to my video channel. Today we will start our work or continue our work on the power supply board. In the last video we have seen that there's a problem with the voltage regulator 24 volt DC. Meanwhile the replacement arrived. So let's start. This voltage regulator will be replaced, and I have seen another problem here. These two caps, capacitors, ceramic caps, each has 10 nanofarad, have a small damage on the surface caused by the pin which comes through the contact holder here, through it, and touches this capacitor. The capacitors are bended down to the board, but they are rather thick and they are damaged here and here. Here and here. This is the input capacitor for blocking the incoming voltage which comes in here to ground. Could be that the overheating rate here is caused by this contact, because this capacitor is grounded. But I didn't measure any electrical connection from here to ground. Okay, I'm not sure. Here we have the same principle. So both have to go. I will replace them by a smaller one, which are not so thick and have more distance to the pins. But now first we will replace this one. The circuit is replaced, and now we can measure the output voltage. It has 24 volt. As specified, the input is, I measure directly at the 34, and here the output is 24. That's okay now. You may ask, how is it possible that the transceiver worked before with this higher voltage? Well, this voltage is part of the PLL circuit and is used to tune the VCOs. There are two VCOs which need a high or rather high tuning voltage beyond 10 volt for better linearity. This circuit, the PLL circuit, also works of course with 30 or 34 volt, because it is stabilized by itself. It has a feedback loop in it, and when the frequency drifts a little bit, the PLL reacts and stabilizes the frequency. That's the principle of such a circuit. So higher voltage is not dangerous. It's only important that the voltage itself is stable, because when we have a rather quick or rather rapid voltage change, fast voltage change, or dips in it, or some other noise, then the PLL is not fast enough to react, and this may distort the output signal. Okay, that's it, and now we replace these two capacitors. The power board is in. The two ceramic caps are replaced, so we have enough space here now between the cap and the pins. Nothing can happen. Totally, we have renewed all the trim pots. This capacitor is new. This voltage regulator is new. And then we can measure the output voltages. Pin 1 minus 4.49, minus 4.5 volt, should be 5 volt, not 4.5. But this is not relevant. This negative voltage is only needed for the selectivity board to switch on and off the filters. There are pin diodes, and the pin diodes use this negative voltage here to be blocked. So when the filter is blocked, the pin diodes on both sides get minus 4.5 volt or minus 5 volt. In case of conductivity, they get the 10 volt via a series resistor. So it is not relevant whether we have here 4.5 volt as we have, or the specified 5 volt. Here we have 24 volt, as we have expected. The other ones are the auxiliary voltages at pin 11. Let's start here, pin 14. This is obviously 0. This is should be plus 5 volt, 4.95, that's okay. This is the DC 10 volt, pin 10. And then here we have the other voltages for the 13 volt input. Here are the auxiliary voltages, 4.3. What is this? Is one of the 1, 2, 3, 4, 5, 6, 7, pin 8. These are the set voltages from the pots here. They are a little bit different from pin to pin. They are not aligned in the moment. This is a passband tuning setting. Okay, the board is working now, and we can focus on the next topic. The next board with some problems is the TR7 board, the digital readout. There are some topics. We have here the problem that the counter should be removed. I talked to the owner. He does not need the option that the internal counter here can be used also for external measurements. So I will delete this connection here and make a wire short circuit to simulate that the counter only has to measure the internal frequency, and remove also the switch on the rear side. That's easy. I see here problem with this tantalum cap. There's a damage. I see some metal or something like this shining through. This one also looks a little bit suspicious. I will swap these two caps, no problem. The other ones could be okay. Main problem of this board are these solder connections. This, because they are also connected on the rear side, on the bottom side, with a lot of connections, but they are not soldered from this side. They are only soldered from this side, and this can cause problems. So we have to resolder it from this side. Here it looks rather good, but I will try to pry off these white plastic sheets and to resolder it also here on this side. I hope this will work without problems. I will do this first and try to pry off these white plastic. Okay, it moves a little bit. It will work, as I see. I found the easiest solution is to heat it up a little bit to make it warm, 50 or 60 degrees Celsius, not too much, but then the plastic will slide a little bit easier over the pins. It's only a question of question of some time, but not to overheat it. Das kannst du vergessen. To get it off. Well, I have to admit I had no chance to get it off without damaging the pins and pulling them out. This plastic is so stiff and there's a very tight connection. When I melt it too much, then I will delete everything. Don't like it, so I have only one chance to resolder it from this side. Look that there's enough solder running in without causing a short circuit on the lower side. I've read in the net from some specialists that it is possible to pry off these white covers here. With this version, I don't think, and I don't want to delete anything. So I resoldered only from this side, and I think this will be sufficient. I will see when the board is in whether we have a problem or not. But I do not try it as long as it is not necessary. Next is to take out these two tantalum caps. They are 47 microfarad, rated with 6 volt for the use on 5 volt. This is not a good solution. I don't know what it is. Is it dirt from outside or does it come from inside? I will see when I have them out. I will replace them with 47 microfarad 16 volt. A little bit better. These two look ugly, so I take them out. Both of these old tantalums measured good. Capacity a little bit more than 50 microfarad. Quality factor is very high, and the DC leakage is 0. That means no leakage. So we could use them. And I think this black dot here, what we can see, is a residue of the polarity marking. Maybe it faded out over the years, but this one, this capacity here has definitely one spot here which is not okay. The enamel is broken, it's a little bit brittle, so it has to go, and this one also has to go. I will replace it by new ones. The new caps are in. Now we can focus on the topic with the external frequency counter. There is a connection. I will take out this pins, this connector, and only, as I said, I will make a bridge to simulate the external switch, but the input now is dead from the external counter option. So this one can be taken out. It was a little bit a hard fight to get it out. It is damaged, but that's not a problem. I looked at the pads are not damaged. This damage here is acceptable for me. I will throw it away, I don't need it. But this is not damaged, so I took it out in the way that the pins were damaged. Well, and now I have to look for the necessary shorted pin. There are two, you see here. Where is it? Two long wires. One is grounded in the case of external measurement, the other one is grounded in the case of internal measurement. This is input of the counter, this is ground. So I have to look into the schematic which of these pins I have to ground. Here we have the schematic. One is ground, 2 is input for the counter, which goes via this transformer into this row of amplifiers. Pin 3 is grounded in case of normal. Normal means internal measurement, and pin 4 is grounded in case of external measurement. And this switch is on the rear side, and the ground is on the rear side directly made to the chassis. It is not fed back to this ground here, which is not so good, I think, but okay, no problem. So I have to measure, or to ground pin 3. Pin 3 has to be grounded to pin 1. This means normal measurement. Pin 1 and pin 3 is bridged. So we have now permanent input, and I measured it on this IC. It's 90, what is this, 9011? U9011. Pin 7 is grounded now, as it should be. That's the input here, which controls this logic. Okay, I will do one further modification here. I have seen we have here the power supply, the input. Sorry, here we have it, not here. That's the power supply input. And in the transceiver there is a weak point. We have 4 pins. 2 are in parallel, 2 are the ground. The center 2 are ground. And the outer one, both outer ones are the plus connection. And they go to this resistor. It's a series resistor. Whatever it has to do there. Okay, anyhow, I assume there's a rather high current flowing over it because it's a power supply for the whole board. In the transceiver we have here 4. We can always connect 2 pins parallel. That means the outer 2 pins could be connected in parallel. This is a plus, and the inner 2 pins is ground. This is good to distribute the current a little bit over the pins, and if one pin gets warm and the resistance increases, then the other pin takes over the current. But in the transceiver we have the problem that this connection here is only, can't see it, it's only with 2 wires. This is a power supply. So I will add 2 further connectors here, 2 further contacts, and add them in parallel. And these 2 contacts I will get from, you can guess, yes, from the switching, which is not needed any longer for the switching of the counter input, which we have bridged. So I can get 2 contacts, they are already crimped, and then I can solder them in parallel to this one. And the power is a little bit better. As I know, in my TR7 these pins are connected in parallel. As I remember, there is it. But here it is not, and I think it's not a good solution because there are 4 pins provided, and why they have only used 2 pins. Maybe there's a bean counter active in this company in those days, and he counted that 2 contacts spare or saved are a lot of money when we calculate about some millions of TR7s. This is not a good design because originally there was provided a 4-pin connection. To show it in the schematic, we have here 2 pins parallel. And here's a series resistor, 5 ohm, 5 watt, okay. I think it's a little bit provided to drop some voltage. The input is, I think, is 12 volt to avoid overheating of the 7005, which would get a little bit hot. So some voltage drop is generated here on this resistor. This indicates me that there's a rather high current flowing in the range of maybe 1 amp or so. I will measure it. I will measure the voltage drop across this resistor, but here are 2 contacts each provided in parallel. These contacts can be squeezed out rather easily. Press it down and then take it out. Number 1 and number 2. They are crimped. I have no crimping tool for this one, I think, or could be, but I don't have spare contacts, so I will use these wires. They are okay, a little bit cleaning, and then I can connect them in parallel. I don't show it in detail. You can imagine what I'm doing. Now we are at the end of part 3 about the series of this TR7. Before I can bring back the TR7 into place, we have to focus on the next work. This is the PTO. There's some problem in the PTO, it is stiff. The tuning mechanism isn't okay, so we have to completely disassemble the PTO. This will be rather challenging but interesting. Stay healthy, stay tuned. See you on this channel.